Hi there, today I'm going to do a video on this new single board computer here, which I'm informally calling the Mini-08 because it's based on the Intel 8008 CPU, which is this 18-pin chip right here in the back. We'll go into some closer views of this in a bit, but let me just give you a little bit of an overview and the motivation of the project right now. So a few months ago I did a video here on the H8 and an 8008 CPU board that I designed for it. I based that kind of on a design I found on the internet by Jim Luce, and I replaced the 8080 board in this H8 with an 8008 board, rewrote the panel monitor in 8008 assembly so we'd have a panel monitor, ran some basic stuff on it. Some stuff like that got picked up by Hackaday. Of course, thank you to all my Hackaday viewers and readers. But then I decided, you know, this is not the most consumable thing in the world because there's not a lot of people with H8 computers. They're still relatively rare to find one on eBay, for example. So why not make a self-contained single board computer? Now, people will immediately say, well, I see two boards there, not one board, but the display board on the front is entirely optional. And like I say, we'll get into some close-up views in a moment, but you can do it with just the CPU board on the back, with a serial port, some LEDs, couple switches, and you know, you can run basic, and you can even run Forth. So I ported a popular Forth interpreter compiler called Jones Forth to the 8008, and I've been doing some of my testing and development now in Forth, and we'll talk about that a little bit. So.
Okay, the schematics will be available like usual on the website, but I'm not going to include them in this video. We're just going to go through a high-level diagram since there are so many different parts to this project. So starting over here, we have the 8008 CPU, and as I mentioned before, it has a triplexed bus on it, and they did that to fit it within an 18-pin form factor. So data, as well as high and low address and some control bits are all on this bus. So those go out and they go to a data bus buffer. This bidirectional buffer can go in or out, and that will directly feed your data bus, so your D0 through D7. But it also goes down here and it feeds a high address latch, which has your high address bits, as well as your two control bits, and the low address latch, which has A0 through A7. Now there's some programmable logic devices that will take the CPU state and will assert these latches at the right time to latch that data. So from that, we get our data bus, and you know, our full address bus, our A0 all the way up to A13. Now, in order to send that to the RC2014 bus, which is what we'll use as our expansion bus and how we'll attach our front panel, and potentially how we'll attach RC2014 cards, we need another couple buffers. So first of all, we need an input buffer so we can read from the RC2014 bus. So bus comes in, hooks to this external input buffer, and that will take data from this bus and put it on the data bus where it can be read by the CPU. But we also need to deal with the outgoing data. And unfortunately, when you're doing port operations, those don't use the data bus. When you do an out instruction, it actually puts it on the address bus. It puts it on A0 through A7. So that comes out down here. Remember, we had this to get the A0 through A7. And I have a buffer down here that takes that and puts it on the data bus. So ins follow this path, outs follow that path. Now, of course, we have RAM and ROM and a couple of page registers. So this thing has 13, it has A0 through A13, which is 14 bits. That's enough to map 16 kilobytes of memory. But I wanted to do more, so I've got 128 kilobytes of RAM and 128 kilobytes of ROM that are supported. And the way that's done is through some page registers. And those page registers use 74HCT670, I believe, is the device. It's a 4x4 register file used in a lot of Z80 single board computers and other modern retro computers used as a page register. So what you can do is you can write to those registers, and they will take the upper two address lines, so A12 and A13, those decode the upper two address bits, and use that to reference a particular row in this address register and give you 4 bits of output. So that is enough for us to derive with 2 of those A12, A13, and A14, and A15. That's 4 bits down there to extend the address space. As well as A16. That will get us up to 128K of address space. As well as a ROM CS, a chip select. So based on setting those two paging registers, we can decide, where it fits into 128 kilobyte address space, plus whether it's ROM or RAM. And, if you look at the code, you can see how this works. So when it boots up, it will actually disable all of this, and it will map the ROM, the lowest addresses in the ROM, to the entire 16K address space on the CPU. But then when the code goes through, it'll set up these registers to point to other things. And amongst other things, we can use that to put several different programs in ROM and have it switch between them, and you'll see me do that in the demo. Okay, there's one last device on the CPU board I wanted to talk about, and that is the 8251 UART. Now, I hooked it up to the same data bus that we're feeding out to the RC2014 because the UART wants that same unified ins and outs on the same 8 data bus pins. It's not going to put up with that, your ins go up here and your outs come from down there. So I put it on this side of those two buffers. And again, there's a little bit of logic to chip selected and such. It goes back to those PLDs. It's a MAX 202 serial driver and a DB25 for your connector. Now over here for the front panel, we've got our RC2014 bus, which serves as the interface between. The 8 address bits come out, A0 through A7, and the 8 data bits, D0 through D7. And there's a PLD that does address decoding. And it takes those various addresses and selects devices. So there's actually many. I only showed 2 7-segment displays up here, but there are 10 of them. So little dot, dot, dot. So it selects, these 10 displays, which one will get written to. So it can write to the DM9368, which will light the 7-segment display. It can also go down here and enable the keyboard encoders. There's 2 of those. They do 4 bits each, so you can read the keypad. We'll also go down here. You can use to talk to the complex sound generator. That's a write-only peripheral. So, select it and then write out to it. And the real-time clock, that's actually a read-write device. Maybe I should have drawn this arrow a little bit differently, but you can both read and write it, and it's another chip select. Not pictured here. There's a couple additional latches that are latched in amongst these chip selects and data bus that hold the decimal points and the blanking status for these DM9368 and 7-segment drivers.
Okay, here is the single board computer. So right here, this 18-pin chip right here is the CPU. You might be used to seeing CPUs be much larger chips on a typical single board computer, but the 8008 is physically a relatively small package, and it multiplexes, it actually triplexes its data bus. So its bus is both a 8-bit data bus, and it's both the high and low address bits, as well as the control bus, all fits into there at different times. We have our ROM socket over here. So right now I have a 28C256 EEPROM, actually a double EEPROM installed in that socket. It's actually wired for 32-pin sockets, so you can install bigger EEPROMs, and this board is designed to use up to 128 kilobytes of memory. And then we also have another socket down here for an AS6C4008, which I believe that's a 512 kilobyte chip. Only use up to 128 kilobytes of it, but it's something I have very common on hand, so I tend to use that chip. You can put a smaller one like an AS6C1008 in if you would prefer. We have power coming in here. There is a place to put a regulator if you wanted to for example, run this board off a 12 volt and then regulate it down to 5. I jumper the regulator across and I power it via a relatively heavy cable that I built myself using decent heavy gauge silicone wire. Don't try to power something like this off of a cheap commodity USB cable. These things are often too small. This board with the display board will draw nearly 2 amps of power. So power comes in there, 5 volts in. I jumper the regulator across. Now the 8008, it does need minus 9 volts. It needs a total of 14 volts. People usually do that with putting plus 5 and minus 9 together. So over here we have a DC to DC converter, which takes the plus 5 and turns it into minus 9. Over here we have the 8251 UART. This is our universal asynchronous receiver transmitter. It gets you away so you don't have to load down the CPU with doing serial I/O. Some of the single board computer projects out there, they'll bit bang the serial I/O out of the CPU. That limits your baud rate choices. That also has you spending a lot of time manually delaying those bits. So we've got the UART there, a Max 232 or Max 202 driver here to drive the real DB25 serial port. On this vintage of project, I really like using an actual DB25, not a DB9, not a header. Nevertheless, there is a 6-pin FTDI header there, in case you want to just hook it up to, an FTDI USB cable. We have a crystal, 4.9152 megahertz for the UART, as well as a divider, and a whole bunch of jumpers here that we can use to select different baud rates. This jumper is currently at 600 baud. Over here we have the crystal for the CPU, as opposed to the crystal for the UART. It's crystal for the CPU, and it divides that frequency in half. So this is a 1 megahertz crystal, gets divided in half. The CPU is clocked at 500 kilohertz. If you get an 8008-1, then you can clock it, I believe, at approximately 1.5 megahertz, divided in two, approximately 750 kilohertz or so. Maybe even go up to 800 kilohertz. Anyhow, there's lots of glue logic around. There are a total of 4 GAL22V10D PLDs that I used. One of them for managing the bus, one for the I/O, one is an interrupt controller, so I actually support interrupts on this board, and then one is an interrupt register. Now, even if you don't use the interrupt feature, if you want to use the front panel, the front panel is still plumbed through those 2 chips, so you need to do all 4 PLDs. Now, there's no magic with these PLDs. These are mid-80s technology, so it's not grossly out of period for what you might pair with an 8008. It's maybe a little bit newer. By the time these things came around, maybe you'd be using an 8080. But these do allow you to really reduce the chip count. And they're just implementing simple gates like ands and ors and nots and such in there. But reducing, each one of these maybe replaces a half dozen individual chips. So it's much more efficient on space to be able to use those PLDs. There are 8 LEDs over here and a latch to hold the LED state. There are also 4 dip switches over here with some pull-ups and a buffer to read the dip switches. Over here is an RC2014 compatible, not completely compatible, but mostly compatible RC2014 40-pin connector. It only does the I/O interface because there's no need to do memory interface on the RC2014 connector because we have onboard memory on the board. Okay, let's take a look at the display board. So up here we have 10 7-segment common cathode digits. They're LED digits. And the reason I chose 10 was I wanted to emulate the H8's front panel, which had 6 digits for a split octal address, 3 digits for a value, and then 1 kind of empty spot in between. So I actually populated that empty spot digit, and that lets you display a 10-digit thing if you wanted to for another purpose. So anyway, we've got those, and then I changed up the way they're driven from how an H8 would drive them. So an H8 multiplexes them, so it lights them individually really fast on an interrupt. That was not very convenient when I tried to do that on the 8008. You end up spending a lot of time multiplexing. So what I decided to do was to implement drivers for each digit. And you can see down there, each one of these digits has a driver. This is a DM9368 or a Fairchild F9368. There's a few different manufacturers of these chips. And what's nice about this is these are hex drivers. So you can give them a 4-bit value and they will light up between 0 and F on the display. And they'll do so without needing dropping resistors. So they have constant current drivers built into them. So you can pretty much just give these things 4-bit values and get your output. And they have a latch enable, so you could just send data, latch it. It's perfect for interfacing. It's much like interfacing a TIL 311 display. So we've got a total of 10 drivers. Now I had when I designed this board, I thought these drivers would be cheap and plentiful and easy to source from China via a place like AliExpress. I found them for about $1.05 each, but I ordered them and I found that all 15 of the drivers that I had ordered were bad, and bad in exactly the same way. And I went back to my junk box and I found some old drivers that I'd bought in 2017. And all 5 of those were bad. They were actually bad in different ways. So some of them clearly defects, but the other 15, those could have been counterfeits. I'm currently resolving with AliExpress, trying to get my money back on that. It looks like I will be able to get a refund on it, but we'll see. It's not a done deal yet. But anyway, you have to be careful buying these DM9368 ICs. I will try to, on the website, I'll try to update data so that people will know where I have successfully found them. But so far, I've found them from a guy here in the States who had some good ones for about $6 each. And it's like five to 6 times as much as you can get them for in China. So it's unfortunate to spend that much. That's like $60 worth of chips for the board. That's too much. I found these Fairchilds from a friend on the 8-bit Heathkit forum. He was able to supply me with those. I may have found some of both the DM9368 and the F9368 on UT Source. I'm waiting for those to arrive so I can compare them and see if they're good. But just be aware that if you try to build one of these, you may have some trouble sourcing those drivers. I do have an alternate version of this board that uses TIL311 displays. Those are also no longer made. They're smaller displays. They have the driver built in. But there is a reputable source in the UK where you can get those for about $3 a piece. So TIL311s are actually cheaper than this chip and display solution. Anyhow, I'll keep people updated on the website. Now over here we have a keypad. So these are, let's see if I can pull one of these. There we go. Standard Cherry MX Blue key switches that you can buy from DigiKey or Mouser. There's a spot on each one. You stick an LED in there, and you can backlight your digits. Now these keycaps came from Max Keyboard. These are ones that the SEBHC Society of 8-bit Heathkit Computers people, they designed for the H8 front panel, and they're actually backlit, so the light shines through. But you'll see that these have symbols for the Z80 registers on them. But like SP here, we don't have an SP on the 8008, not exposed to us. But anyway, so the keycaps are a little bit pricey, but they're backlit, they look cool. And they're, with Cherry MXs, they're easy to type. Keys feed into a couple of buffers where you can read them with their associated pull-ups. We have over here dropping resistors for the LEDs, a jumper to turn the backlighting on and off. So you can pull your keyboard and tell whether a key is up or down. There is a PLD here that handles all of the addressing for this board. So we've got, different I/O ports associated with the digits, different I/O ports associated with reading the keypad. The drivers, you can actually tell them to blank a digit. So we have 10 bits of blanking information and 10 bits of decimal point information, so we can light the decimal points. Those additional things that are buffered like that, I believe they went to 74 LS 273 latches that hold the blanking information, the dots, stuff like that. So the other thing I decided to do, kind of similar to how the Heathkit H8 does it, but I have the display board ask to be refreshed. So even though, we're not doing multiplexing of these digits, it still does ask periodically to say, if I'm displaying a memory address on here, go update the display to that memory address. So there is a crystal here for that, and a clock divider, and so periodically it will generate an interrupt request to the 8008 board that says, go refresh this display with the latest data. So that is why there is that oscillator there and a clock divider to go with it. So that gets us through everything, about this much of the board that implements the display and the keypad. I had a little bit more room here, so I put a bit more stuff on it. And what we have here is an RTC 72421 real-time clock chip. Again, something that's popular with the SEBHC guys, so I chose it. It has, it doesn't need an oscillator, its oscillation is built in, but it does have a spot for a battery, so you can battery back up that clock. And that will allow us to implement a clock on this particular board. So I had a little bit of room left, so I decided to implement a sound on board. So I have an SN76489 CSG, the complex sound generator. I believe it's the chip used in the Tandy 1000, maybe used in something like the ColecoVision. A relatively easy to program. It's 3 voices of notes plus 1 voice of noise generator. So like a 4-voice chip, programmable over 8-bit. Do need another latch to hold the data that we're latching into it, because it's needs to do a little wait state thing. So we've got that CSG. There's a single transistor amplifier that I put on it, enough to drive this speaker at very low volume. There's also a header over here if you want to hook up external amplifier. Now, to sandwich the 2 boards together, I decided that I would go like this. Let's see, so you can see it. And, you know, mount one upside down on the other. That gives you kind of a compact footprint. Your 2 connectors come out the side. You still see that? Yeah, you still see that. And then I made a little bridge board here that plugs in and ties them together. You could also, if you wanted to do, you could do piggyback headers, you know, vertical headers, vertical socket, hook them together that way. If you build one of these, it's up to you. Okay, let's give this a shot and try it out. I'm going to aim for an authentic experience using my Heathkit H9 terminal. So rather than using the modern computer or the propeller serial terminal or the LCD display, we're going to go old school and use this thing. And what's nice about this H9 is it has no CPU in it. It's implemented entirely with TTL logic. So it's got you know, some ICs that take incoming characters and put them into RAM, and other ICs that pull them out, run them through the character generator, and display them on screen. It's limited to about 600 baud, and that's because it actually reads the characters during the screen refresh interval, so it can only process like 1 character per screen refresh. So we've got the single board computer hooked up to it. It's set for 600 baud. Let's go ahead and turn on the computer. And there we go. It's the same monitor I used in my H8 8008 project, so it should look kind of familiar. Kind of says the same strings on it. I don't know how much flickering you're going to get on the display here, but let's try it out, and we'll just play with it a little bit. You know, maybe we'll do some other demos, you know, with the screen capture on the real computer, just so we get a little bit better experience. But for now, let's see what it looks like, authentic, as if you'd have been running an 8008 based computer with a terminal like this back in the day. Okay, so the monitor is up. Let me do a so let's try basic. I'll hit B for basic. It says you know, hit SCR to initialize program space. That's important, otherwise it will glitch. And let's just do a quick program. 10. Sorry for this slow typing, but I am typing left-handed. Whoops, that was not right. So Selby Basic, I don't think actually interprets backspace. We'll see what happens. Maybe it'll work. Return. Let's put in a for loop. And let's run it. Does it run? We'll see whether that typo there actually caused a problem or not. Yeah, well, my plus sign ended up in there, the typo, but you can see it, you know, slowly printing out the output. Let's try a few other programs. Here, I'm going to reboot again. Now, one of the things I did is I ported a 4th interpreter to this. I don't know if you call it a fourth interpreter or a fourth compiler, but it was called Jones Fourth, and there's an implementation for the x86. I ported it to the 8008 so that we have fourth here and we can try it out. Okay, so let's do a quick fourth program. We'll create a new word called Scott, and I'm just going to have it print out Scott was here. Let's close that quote. CR colon. And that's how you create a new word in Forth, is you start with the colon, you put your new word, you put your statements that comprise it. So we've got the little print a string statement and the carriage return, and then a semicolon to close it. So we'll do that. And then let's create another one. We'll call this one 10 Scott. And then we'll do a 10 0. This is how you do a loop, like a for loop in Forth. And it can do Scott and then loop. So 10 0 do Scott loop. That seems right. Now let's run 10. There we go. So Forth is actually the second programming language that I learned, and I learned it right after learning BASIC. And then someone gave me Turbo Pascal, and I learned Pascal and forgot all of the Forth that I've ever done until now. So this is based on a Forth implementation called Jones Forth. Jones Forth is written for the x86. I ported it to the 8008. And when I say ported it, I mean I pretty much completely rewrote it. But you know, one of the nice things is you can actually do things like decompile the program. So let's decompile 10 Scott. I mean, Forth, and this decompiler is actually written in Forth. You know, you can write stuff in Forth that operates on Forth. So look at that. So 10 0 do Scott loop. Cool. Now Forth is a stack based programming language, so if I put some words on the stack and .s will print the stack, let's do that, and it gets 3 2 1. So the head of the stack is over there, the tail of the stack is over there. You know, we put them in 1 2 3, so it ended up from, you know, first in last in first out, so 3 2 1 order. And you know, if you want to do, you know, an operation, you know, like plus, and now let's look at the stack after executing a plus. You know, it took the 3 and the 2, it added them together to make a 5, and that's, you know, your basics of Forth. So a simple stack-oriented language. We've got a variety of built-in words here, and it actually prints the words that we created. So you could just go along, you know, creating your own words. This was kind of cool back in the day. You know, what if you're moving from something like BASIC, where you haven't really, the old BASICs were just line number oriented. You really didn't have the way to have like named subroutines. This was kind of neat. Reboot here again, and I have a third program loaded in here, which is, let's wait for it. Do you want to go on a space voyage? Yes. And it's Star Trek. And I don't even know how to play Star Trek. You know, there seem to be commands to do like sensor scans, and let's see if we can do something interesting.
Okay, I brought it over here. I've hooked it up to my Windows machine where I can run a terminal emulator and do things a little bit quicker and a little bit clearer than I can on that H9. So let's go ahead and boot the computer. It makes a little bit of a noise there at start, and that was just the CSG chip outputs random noise until you send a value to it to reset it. So the computer started up as usual. It's just printing the timer. Over here in the terminal window, we can see that we got the usual menu displayed. But what I'm going to do is I'm going to do a little bit of forth programming because I put a lot of work into the forth interpreter compiler here. So let's go ahead. We'll switch to bank 2. And here we are in forth. And I've added some commands to use the I/O port. So for example, first of all, let me switch into hex. Okay, I've switched into hex mode. Now let's send some commands and try to light these LEDs on the side. So it's as easy as saying FF to port 8 and out. Remember, forth is stack oriented. So, you know, what's going to be on the stack, the first element will be an 08, and then the one after it will be the FF. So do that. We've lit up all of our lights. So like 3308 out. Simple as that. Whoops. Let's fix that. There we go. Turned our lights off. If I wanted to read from the switches, I would just do the same thing with an in instead of an out, like 00 in, and then you have to use a dot. Dot is to print. So F9 is what's being read from the dip switches. That's a little bank of 4 dip switches on the back. I'm not going to flip the computer over to look at the other side of it. But let's do some more things. So how about a simple program to exercise these LED displays? Okay, so first I'm going to do a bunch of constants. These are going to define the various ports that we'll be accessing. And now I'm gonna output some values. First of all, let's finish that. Let's go to this .0. This is one of the shift registers that holds the dots. So there we go. I turned in those dots. And then there's another shift register holds the blanking. Yeah, let me fix that. The blanking. So let me do that. I've turned on all those. You know, you can see there's some random data sitting there in the in those LED displays. We'll fix that in a bit. And then let's turn on. There's one more set of addresses to do those upper 2 digits. So I've turned on their digits and their dots. Now, want to send something out to one of these? Let's send an 88 out to digits 8 and 9. So it should be those two. There we go. There we go. Set all the digits. Now watch here. I can set them all to different values. And let's do a little program. So what this is a for loop that goes from 0 to FF, puts the index on the stack. So it'll put 0 to FF on the stack, puts the digit 0 port on the stack. I messed it up again. Look at that. Test 0 do FP dig 0 out loop semicolon. There we go. It's what happens when you try to do a demo, you forget a few things. Okay. This time it's going to work. I guarantee it. There we go. So there you see, we're writing those values out to that. And, you know, you run test over and over and over again. You get the idea. So it's relatively easy. Forth is a relatively easy language to do this sort of programming. And it looks like port 4 is the keyboard. So if I do let's do 4 in dot, that will read port 4 and print it to the screen. FF, no keys are pushed. Now let me push the 0 key, and let's do 4 in dot 4F. So that is it is reset some of the bits, so they're sort of active low. There's a little table in the documentation that'll tell you you know, what the various scan codes are for the keys, but that was the scan code for the 0. So keyboard working as expected. Let's try out the real-time clock. Now I'm going to paste a relatively long forth program here to the screen, so just bear with me. We are actually running at 2400 baud, and we are using flow control, so it does take a couple seconds on some of the more complex statements for the forth interpreter to compile them. So what we've done is I've defined a bunch of constants for how to read from the real-time clock. I've created some words that allow me to read and write the ports. You can see some stuff for how to read the seconds, how to set the seconds. Okay, I've got all of my fourth words in there. Now let's do clock once term. So this one I defined up here. It gets the hour and it prints it out as 2 digits and a colon. Then it does the minute. It's 2 digits, colon, et cetera, et cetera. So it's going to print the clock to the terminal. There we go. 8:21. So 8 minutes and 21 seconds. I don't have the battery installed, so the clock resets every time you unplug it. Now let's do clock once. This one should print it out here to the display. There we go. Here, is there, do I have something that resets? Let's do disp enable. So I've got a function here that should clear all of the stuff I don't want on the display. So there, I turned off the digits I don't want to be seen. That was the disp enable. Now clock once, 9:01. So it's counting away. Now if I run clock forever, this will just sit in here in a loop. Here, let me first turn off these dots. They kind of annoy me. Where's my FP test? Let's 0 FP dot 0 out. There we go. Now let's do clock forever. So now we have a clock on here. Simple as that. Now, my fourth implementation here, it doesn't actually understand Control C. It is dutifully going to just run this forever, and you'll never be able to break out of it. So we'll just reset it, because I want to show you some music, because we have this CSG chip over there. So let me find my sound test. Paste a whole, well, I'll paste it in sections so you can see it. So first, let's set up all kinds of constants. So what we have here, this 1,1 is the constant that's for the port. And then I'm defining a bunch of constants for the frequency, the timing constants that you send to the chip for the note. So I had to learn a little bit about music to do this. I had to learn, about octaves and notes and frequencies. There's a table tells you the frequency to set for any note. But the way this is working is this goes note, octave, and then sharp or flat. So like a C4S, C in octave 4 sharp, or a D4F is D in octave 4 flat. So I've got next some statements here that will send stuff to the sound port. So here, this first one sets the sound. Let me hit return. So it basically sends part of, you have to write the sound as 2 bytes, the frequency, with these 76489 chip. So it first sends I think it's the low part of the sound, and then the high part of the sound. It sends those both to the port. This one here is for setting the attenuation. Now 0 is loudest and F is highest. And then there's a word here I defined called quiet, which just makes everything stop making noise. I have some words here that are set up to output notes. And basically it takes whatever frequency is on the stack and it sets it to play a tone for a certain amount of time. So these are always specified in fractions of a note. So like a note 2 is a half of a note. 4 is, why does my terminal keep doing that? Note 4 is a quarter note. Note 8 is an eighth note. We've got some pauses here. Let me get those pasted in. Because sometimes you just want to wait and you don't want to play music. And then some songs. So let's first paste in Mary Had a Little Lamb. So you can see what I'm doing is, I'm setting like a G in octave 4, 8th note, F in octave 4, 8th note, E in octave 4 flat, 8th note, etc. Let's do a couple more. Got William Tell. And one last song, which is America the Beautiful. Okay, let's do this. Let's do Mary Had a Little Lamb. And let's do William Tell Overture. Now the tempo is going to sound off on this, and part of that is because I'm running this as a fourth program, and the program itself has some overhead. So even though I'm trying to do like 16th notes, it's a 16th note with like some slow language processing involved. So let's hear it. It'll be a little bit slower than you expect. Okay, that was William Tell. Finally, America. Okay, yeah, and I just got those 3 songs from some old Basic A music for the old IBM PC. And I want to send, I can do this, it'll be like a phaser sound, so yeah. Here we go. Okay, so that's a quick demo of the sound capability. I only used one voice, and I didn't use the noise generator at all.
Well, we'll just go back. We'll do front panel test again in case it looks better on here. So this is front panel. It starts up always displaying a counter that is sitting here at memory 037333. That's sort of the next to the least most significant byte. If we go back one, there's the most significant byte. This counter increments every time that the front panel asks for a display update. And then, most significant byte, it'll take a while to get there. We can change addresses, so mem 111.222. We can alter what's in the addresses. 333 automatically advances, so go back, there's your 333. We should be able to read a port. Let's do mem 000 and 001, why not? And then if I hit the end button, there. So yeah, port 1 has a 2 in it. Basically your front panel. Let's do 011 and let mem 011 010. Now this should, if we hit out, it should send 011 to this port here where the LEDs are. There we go. Just like it should. So you can use the front panel to enter programs, examine memory, send and receive from I/O ports, etc. Okay, in conclusion, I hope you enjoyed this video on my new Mini-08 computer. A single board computer with its optional display board. I will be putting the Gerbers and the PLD files and everything else that you might need to build one of these yourself online, in case anyone else wants to build one. Thank you very much, and please subscribe. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.